Ladies and gentlemen, good afternoon. Welcome to CarbonTech Global 2020 live webinar, Development and Application of Green Composites. I'm the host, Bella. In the live webinar, the speakers in the green composites industry will provide the latest development and application of green composites. CarbonTech Global is a technology service company that focused on the research of the carbon materials industries and promotes the integration and innovation between carbon materials and strategic emerging industries. This webinar has 4 PPT presentations and a roundtable discussion. It will start at Beijing time at 15:30 and it will last for 2.5 hours. Please arrange your time and your work in advance. This seminar invited 4 industry experts in the field of green composite materials. Dr. Alaa, the chairman of AMST Teknoloji, Dr. Hatem Abushammala, the Wilhelm-Klauditz Research Fellow at Fraunhofer WKI, Dr. Niklas Garoff, the Business Development Manager at Stora Enso, and Dr. Mårtensson, the CSO at Bcomp. If you have any questions during the webinar, please write it down at the Q&A part or raise your hand at the roundtable discussion part. We will help you to open your microphone to talk with the speakers. Now, please allow me to introduce our first speaker, Dr. Alaa, the chairman of AMST Teknoloji. Dr. Alaa, expert on the development of polymer-based advanced materials. He has over 25 years of experience in polymer synthesis and in the preparation and evaluation of composites and nanocomposites. He is heavily involved with industrial projects and with several manufacturing organizations. He is receipt of several grants and published widely in the field of nanocomposites. He is also the chairman and founder of AMST Teknoloji, work as a researcher at CMRDI, Advanced Material Division, Composite Lab, head of polymer composite, and a nanocomposite research group from March 2012. The topic of his speech is development and application of green composites. Let's welcome Dr. Alaa.
Hi. About green composite, in recent years, the development and use of green composite materials are gaining importance in the field of aerospace, automotive, and marine and other industrial applications because of their potential properties such as higher specific strength and better corrosion and fatigue properties than most of metals. The ever-increasing temperature on our Earth's surface and the use of non-biodegradable materials for industrial applications leads to increase in global warming, which forced the researchers to work on green composite that suit the properties and the reliability of the metals, alloy, and composites. The increase of use of non-biodegradable polymers increases air and water pollutions. Development of green composites help to maintain ecological balance on our Earth. Our speech today will be focused on discussion the green matrix materials applications and modifications, the challenges and applications in some fields, natural fiber plastic composites, packaging and automotive, and our roadmap for development of such applications. Composites is a material, it's a combination of two or more components to produce a new materials with unique properties. It's a tailored materials. Green composites are the combination of natural fibers with bio-based polymers or synthetic polymers. Green composites are biodegradable, so they can be easily decomposed by the action of microorganisms when dumped. They are converted into H2O, it's water, and carbon dioxide. Economically concern, especially after COVID-19, have resulted in renewed interest in natural materials like green composites. Also, the recyclability and environment safety are becoming increasingly important to the introduction of materials and products from green composites. The added value of the green composites, it's economical aspects and social and environmental. Economical aspects, it's cost reduction of waste treatment, activation of commercial area, more jobs. Many citizens may feel pride for their community, good environment, education, and high style of life. So it's a business for lifestyle or better lifestyle. Environmental aspects, it's a reduction of the emission of carbon dioxide, which generates the global warming phenomena. The composite, it's on the according the matrix, we have polymer matrix, metal matrix, ceramic matrix. Polymer matrix consists of thermoplastic matrix and thermosetting matrix. The thermoplastic is some of thermoplastic biodegradable, some of them non-biodegradable, such polyamide, polylactic acid, polyglycolic acids, polyvinyl, and starch, and many other polymers. Non-biodegradable, such epoxy, lignin, natural polypropylene, polyethylene, and PVC. The biodegradable, like polylactic acid, as we see, it's from the origin, from the corn lactic acid, from polymerization of lactic acid. Also, the epoxy, we combine epoxy or polyester or polypropylene or polyurethane to make such composites. The reinforce between these composites and fibers. The fiber, we have natural fiber and synthetic fiber, or man-made fiber. Natural fiber, like vegetable fibers or animal fibers. Man-made fiber, it's synthetics like glass fiber or carbon fiber or any other fibers. This is, we see some natural fibers which we can use as a reinforcement for our green composites. Natural fiber composites or reinforced composites, as we told before, some polymers non-biodegradable, some polymers biodegradable, some polymers synthetic, some fibers, and biodegradable polymers and natural fibers. The combination of these fibers, as you see here, and this is non-biodegradable and partially degradable and fully biodegradable composites. The challenges or technical challenges which we faced when we make or produce or develop any products from composite at all, and especially green composites, is many challenges. The most of them is the wettability and the homogeneity of the components of the green composite. To overcome these composites, so as we see, composite, natural fiber composites consists of natural fiber and polymers, and then we produce green composite pellets. We use some method for modification of the surface, because the natural fiber itself is hydrophilic, so it's like water. And the polymer, it's hydrophobic. To combine these, we have a challenge to modify the surface of natural fiber. So we use some compatibilizers or some functionalized polyolefin as a coupling agent to make a good wettability and good compatibility to give a strong bond between the fiber and the polymer chain. As we see, we can use in natural fiber plastic composites, wood dust or wood fiber or rice husks or any other natural fiber. With a plastic, we produce wood pellets or natural fiber pellets. This is, we can say it's a liquid wood, green liquid wood. The content of natural fiber can be up to 70%. The manufacturing of these polymers or this green composite, we can use extruder, twin extruder, twin screw extruder, or we can use also the press mold technology. Also, we can we can produce multi-layer or monolayer. Multi-layer can be homolayer layer or heterogeneous layers. So we can use natural fiber with glass fiber also as a layer between together and submit together in the mold, and we produce a new materials. Also, we can use additives, some steric or compatibilizers, antimicrobial, blowing agent, foaming agent, colorants, functional fillers, and nano reinforcement. The applications, traditional applications, there are some traditional applications and some advanced applications. The traditional applications is in construction and in some other in decking and in parquet and many other applications. As we see, advanced applications, automotive and aerospace and other applications. The application of the formula of such composite depend on the application. If we will apply these materials indoor, so we formulate the formula according to the application. We added some additives if we produce materials for outside, so we add some additives to anti-IR according to the sunlight to prevent the decay of the material. This is the scheme of how to produce. We can also produce these materials from virgin materials, virgin polymers, or from recycled polymer. As in the slide now, recycled materials we collect and we make pellets, also the sawdust. And one of the most challenges also is the natural fiber like water. So the water content must be dried to up to from 2 to 8%. And after that, we combine them to make wood or natural fiber panels. And this is the machine, the most important point in these materials, that we produce liquid wood, which we can use it or produce it through plastic machines. And we deal with these materials as a wood. This is the mechanical and the physical properties of green wood or natural fiber plastic composites or polymer composites. As we see now, the mechanical properties of these materials is higher than the board materials or MDF or HDF. So it's a new material. It's a magic material. The benefits and advantages of these materials: we can produce material anti-fire and waterproof, and we can deal with this material as wood material, but it's not wood. It's look like wood. It's a combination between the properties of plastic or polymer materials and the fiber or natural fiber materials. As you see, also we can deal with it as a wood. Different color, different shape, different formula, different application. Also, the benefits of these materials, it's low moisture absorption, safe from cracks, resistance to root, safe from wrapping and anti-termite. The disadvantage of these composites, decolorization, and may not look real, and sometimes the weight is more, but we can overcome this disadvantage by use foaming agent to produce lightweight materials, flexible in hot weather and rigid in cold weather. And this is some products and some applications of such materials. We call this natural fiber plastic composites or green composites. Also this is some products. And the market of these materials in US dollar by 2024 it will reach $130 billion with CAGR 7.8%. Green composite market it's expected to achieve 11% CAGR during 2023. This is a SWOT analysis of these materials, the strengths and weakness and opportunities and threats. The high pollution and cheap labors and these materials, for example, in Egypt, we have every year more than 30 million tons of natural fiber or agriculture residue. Every year 5 million ton rice husk, million ton of bagasse and other materials. So it's very, very good opportunities to make a good business in such materials in many countries. The advanced applications of such materials, green composites, not only natural fiber plastic composites, the green composites also can be applied in automotive or in functional materials such antibiotics, home appliances, hard tool materials, in agriculture, in medical drug delivery, in cancer detector, MRI contrast, and UV protection. Also, one of the applications is the food packaging materials. Also in electronics, the application of electronics of these materials is promising. For example, in green composites in food packaging, protection from contamination during slaughter, post-processing, distribution, delivery, storage, retail, display. The economic effect of using of green composite in food packaging is the save of human life. It's food. It's a key factors in relating business. Freshness of the materials of the product and on the shelf, and the shelf time also is a main factor for selection of packaging materials. The food safety and the health of human also, so we can reduce the medical cost. This is, we produce some materials, nanomaterials, for applications in film, packaging film, to prevent the deterioration of the food during the shelf time. As you see now on the slide, the banana, after 7 days and sometimes after 2 days, it become black. And also the apple and bread and meat, all of these products need to make some protection. This is the conventional packaging materials, polyethylene. And as you see, this is the first day. After 4 days, 5 days, 6 days, 7 days, and after 7 days, what happened? Let's see. This is what happened for the rice after 8 and 12, 11, 13 days. Deterioration, it's poison. Big problem. How to solve this problem? We produce polymer materials, biodegradable materials with nano particles. So we make antibacterial packaging with composite with nano silver and nano copper. And also we use nano clay as a anti-barrier or barrier materials to decrease the barrier materials or barrier properties of the materials. As you see, this is the first day, 4 days, 5 days, day 6, day 7, day 8, day 11, 12, and what? Oh, 13 also, 14, 18, nothing. So the material, the food is reserved and healthy. Also, this is the experiment we make for apple. Apple with a conventional packaging. This is day 1, day 2, day 3. And after 7 days, the problem is day 14, day 18. What is about antibacterial packaging with apple? Day 1, 2, 3, 4. Oh. Day 13, 18. This is the achievement of science, and we make something like which we can firstly prevent the deterioration of the food, and we increase the shelf time. It's a breakthrough and a good achievement to save health of people and to make good money. The sustainable development of any business, the main target of the business, not only to make money, but also to sustain, but also to serve the health and the money of people. Another applications is the automotive industry challenge. In the automotive industry challenge, as we know, we have a big problem, environmental issue, importance of the carbon footprint as design parameters for improving the fuel economy and conventional gasoline-powered automotive. So the increasing of carbon dioxide emission, lack of strong decarbonization targets, we need safe vehicle, energy efficient, and energy low energy consumption and safely. We have a plan for 10 years, 5 years, and 10 years to produce such materials to make green composite for automotive using of graphene and carbon nanotubes and some other additives. And this is our target, to make a full recyclability, lightweight, full efficiency, improved safety, profit growth, and all this is the body of car will be green structure, enhanced material impact performance, high volume demonstrations, and the technology, better processing and automation, rapid repair strategy, more thermoplastic composites. And we have a fantastic experiment how to combine the thermoplastic and thermoset together to make some elements, some like bumpers with a good energy absorbance to prevent the life of people inside the car. This is our technical partnership. Our AMST is a staff R&D lab, pilot plant. We work together closer with university, with the technical centers, technology centers, and also with the industry. This is a product creation phase. Firstly, development, technology invention, laboratory prototype, industrial demonstration, industrialization, and commercialization to the market. And at the end, we want to thank all of you, and we want to say, please, the agriculture residue is like diamond. So stop to burn the agriculture residue and start changing it to wealth, from waste to wealth. Thank you.
Thank you, Dr. Alaa. Yeah, that was a very wonderful speech. And we found out that there are some questions at the Q&A part. So we would like to leave these questions to the end of the webinar about the roundtable discussion part. Thank you a lot, Dr. Alaa. And now, let me introduce our next speaker. He is Dr. Hatem Abushammala, the Wilhelm-Klauditz Research Fellow at Fraunhofer Institute for Wood Research, WKI. Dr. Hatem Abushammala is a materials scientist with 11 years of experience in the field of bio-based nanomaterials and polymer with a focus on nanocellulose. Until recently, and from 2017, he was the laureate of the prestigious Wilhelm-Klauditz fellowship from the Fraunhofer Institute for Wood Research in Germany. Dr. Abushammala has 3 patents, applications, and 20 research articles on the extraction, modifications, processing, and application of cellulose and nanocellulose-based materials and composites. He is a frequent reviewer and a broad member of several international journals in the field of bio-based materials and polymers. The topic of his speech is from biomass to high-value nanomaterials, a focus on nanocellulose. Let's welcome Dr. Hatem Abushammala. Hello.
Thank you very much. Thank you very much, Bella, for the introduction, and thank you everyone for attending this series of webinars. Coming to my part, the current environmental concerns generate an increasing interest in the extraction and processing of bio-based materials and polymers. Among these, nanocellulose has shown a great potential in a wide range of applications, from automotive industry to tissue engineering, and water treatment. So today in this webinar, I will try to take you in a fast tour in the world of nanocellulose with the 20 minutes I have. But before that, I would like actually to give you an idea about the situation of lignocellulosic biomass, especially in Europe. So if we really exclude standing forest and food crops, and we will find that we have like 4 major lignocellulosic residues. Forest residues, crop residues, industrial residues, and municipal waste. And when I talk about forest residues, I talk about the residues of trees when these trees are harvested in the forest, which include like branches, trunks, and crowns. Crop residues are like really clear from the name. Industrial residues, I'm talking here about sawdust, pulp reject, and bioethanol residues. And obviously also we have like paper waste and municipal waste. So when we talk about amounts in Europe, we're talking here about tens and hundreds of millions of tons generated every single year in Europe. And I don't want to talk specifically about numbers here because these numbers are not very, very recent, but you can really have an impression about how much actually lignocellulosic residues are generated every year. In terms of how much of these actually generated residues are available, we still talk about tens and hundreds of millions of tons every single year. Actually, some of these residues are even burned to produce energy for certain chemical processes, which is obviously not the most green, most effective way of utilizing these residues. Also, in the pulp and paper industry, there's a strong drop in the paper market, obviously due to the improved recycling techniques, technologies, and extents, and also due to digitalization, which makes pulp as one of the promising starting materials to utilize for making certain green materials and composites. And although it's not really the topic of my talk, but also I have to highlight the potential of lignin, which is a byproduct of pulping industry. And every year there's tens of millions of tons are generated, most of which actually is burnt for energy, similar to many other wastes, industrial waste. So we can say in general, there is a strong need for a strategy or technology to develop high value functional materials out of pulp, lignocellulosic residues, and also lignin. Now, I don't really want to go in detail into wood structure and all these anatomical features, but we all know that wood in general is made of lignin, hemicelluloses, and cellulose. And in pulp and paper industry, usually lignin and hemicellulose are taken away through standard and traditional pulping processes to produce 20 to 40 micrometer thick cellulose fibers. Out of these thick fibers, we can make one form of nanocellulose. It's called cellulose nanocrystals. These nanocrystals are crystalline, rod-like nanoparticles with a thickness of a few nanometers and a length between 100 to 200. For sure, there is even longer nanocrystals than these ones, but let's say this is pretty much the standard. These cellulose nanocrystals are produced by treating pulp fibers with a strong acid such as sulfuric acid in a chemical hydrolysis synthesis routes. The other form of nanocellulose is cellulose nanofibrils, and these fibrils are semi-crystalline, spaghetti-like nanoparticles with a thickness of few nanometers up to tens of nanometers and a length in the micrometers. And these cellulose nanofibrils are produced by mechanical fibrillation of pulp fibers. So in general, there's no chemicals used in such processes, or at least small amounts. So if you can't remember the names, you can remember them as rice-like nanoparticles or spaghetti-like nanoparticles. Now, why nanocellulose in general is interesting? Because of so many properties nanocellulose have. Some of these properties nanocellulose has inherited from cellulose itself, such as biodegradability, for example, and low density. But nanocellulose has high mechanical properties, which is around 100 to 200 gigapascal, we're talking about youngest modulus here, which is pretty comparable to carbon nanotubes and steel, with a pretty low density of around 1.5 gram per centimeter cubic, it's even actually lower than that. And what's very interesting here, and what's very interesting about nanoparticles in general, is the very high surface area. We're talking here about 250 to 500 meters square per gram. And this high surface area, what makes nanoparticles actually are way more effective than macroparticles such as cellulose fibers. Also, nanocellulose lends itself to a wide range of surface modifications due to the abundance of hydroxyl groups on the surface, which make them easy to functionalize and making so many kinds of functional nanocellulosic materials. And also due to their size and surface charge, nanocellulose can form one-dimensional, two-dimensional, and three-dimensional very interesting liquid crystalline structures, which are very interesting for optical applications. Due to these properties, nanocellulose has been explored in a wide range of applications. Like, I cannot even cover like half of them in this talk. We're talking here about tissue engineering, wound dressing, pharmaceutical formulation, for making lightweight composites for automotive industry and aerospace industry, for water filtration, and also in electronics, although nanocellulose itself is not electrically conductive. Due to these properties and this great potential, in the last 10 years, there is an increasing interest in the academia and industry in nanocellulose. So imagine just like 11 years ago, in 2009, there was only 200 publications about nanocellulose. And when we talk about 2018, we are talking here about around 2,400 publications. So there is a very strong interest in nanocellulose, which also led to the establishment of more than 20 production sites for nanocellulose all over the world, especially in Europe and in US and Canada. There's also some information here about the price. So the recent prices of nanocellulose is around 200 to 500,000 euros per ton. These prices obviously are high, but there's a future estimate that it will go really down to 10,000 or 20,000 euros per ton, which is pretty decent a price compared to some other functional nanoparticles. And this is for sure will come with the introduction of more nanocellulose-based products in the market. What's interesting also in the market that it's growing really, really fast. We are talking here about a growth of around 20%. Now I will give you just a very fast idea about nanocellulose production, and I will not talk in detail about the process because there are different processes for making nanocellulose. But overall, for cellulose nanocrystal, the standard method is using strong acid hydrolysis, mainly with sulfuric acid. And in such a process, actually, the amorphous regions of cellulose are dissolved through hydrolysis by the protons of the acids, and the cellulose crystallites are liberated in the form of cellulose nano crystals. And for making cellulose nanofibers, usually the pulp fibers are mechanically fibrillated using a wide range of techniques such as homogenization, microfluidization, and microgrinding. And here, most of these methods tend to apply strong shear forces on the pulp fibers to make these cellulose nanofibrils. One observation here, if you can notice, that nanocellulose is mainly made of a pure or almost a pure sources of cellulose. And since I mentioned that there is a great potential in lignocellulosic residues, what if we can make actually nanocellulose directly from wood and directly from lignocellulose? Because sometimes maybe some of these residues, there is no point actually to pulp them. So this was actually part of a work I've done around 5 years ago. And I would like really to share with you, but it was not really very surprising for us that there's no such a process to make nanocellulose directly from wood and lignocellulose, because it's not really easy to find an agent that can dissolve lignin, can dissolve hemicelluloses, and also dissolve the amorphous regions of cellulose selectively without destroying the cellulosic crystallites. And such a job is really difficult to achieve at the time. Now, for that purpose, I actually proposed the use of ionic liquids. Ionic liquids are green liquids. They are actually salt at room temperature, and the main reason for that, they are actually made of big cations and anions, such as the ones you can see here, imidazolium, pyridinium, and usually big also or small anions. These ionic liquids are very interesting in the last 20 years because they are considered green, although this statement is not really 100% right, but could be recycled and reused to a certain extent. But what is very interesting for me and what's the main reason I use them is that ionic liquids, they have varying interaction with wood polymers and with all chemicals, depending on what kind of cation and anion you use. For example, if you change the anion, you can get a very different ionic liquid. If you change the cation, the same story. So there's pretty much unlimited number of ionic liquids that could be synthesized. For this purpose, I chose one certain ionic liquid, which is one of the cheapest ionic liquid. It's called 1-ethyl-3-methylimidazolium acetate. And this ionic liquid has been used to treat wood in general. So it can dissolve wood really efficiently, has high affinity to lignin, which is usually the most recalcitrant biopolymer in wood during pulping, and also has the ability to hydrolyze amorphous cellulose. So I developed my process based on that. And in this work, I used an Amazonian wood from the Amazonian region, since this project was a German, Brazilian project. The wood is called Anguin vermelho, and we treat it with the ionic liquid at pretty much mild temperature and time. And then the pulping liquor was separated simply by centrifugation, and then we got this wood residue. And we noticed that we were able to actually pulp the wood pretty much efficiently. So around 90% of the hemicellulose were removed, and around 70% of the lignin was removed. We repeated the process a second time to remove the residual lignin. So we were able actually at the end of the day to remove around more than like 90% of both lignin and hemicelluloses, while a small amount of cellulose was degraded, hoping that this part actually is amorphous cellulose. We bleached the residue, and from these both pulps, bleached and unbleached, we were able to extract nanocrystals. And here we go. So the pulps I produced from this process, unlike traditional pulps, they are highly dispersible in water. The moment you just put them with very mild sonication, you can get really very nice suspensions, as you see. This is obviously not the case using like pulp fibers. If you bring pulp fibers, any one of us, and try to disperse it in water, that's not going to be the case. They will immediately precipitate. And obviously, we confirmed this with the microscopy, with atomic force microscopy, and you can see the rod-like nanoparticles. And we were able to confirm many of the parameters of these nanoparticles. And also very interesting here that we make a special kind of nanocellulose, which is lignin-coated nanocellulose, which also has a certain potential in certain applications. So overall, I can say we have a process here to extract nanocellulose directly from wood, which would be very interesting to apply on lignocellulosic residues. Now, this process has the advantage over the traditional sulfuric acid process that starts with wood. In terms of yield, we can get like 2 to 3 times the yield which we get from standard process. But obviously, will be needed more thorough assessment of such kind of processes. But what's also interesting that the hemicelluloses and lignin from this process, you can collect them and fraction them easily actually, and you can use them for making other like maybe biomaterials. And it's also applicable to different lignocellulosic waste and residues, which was actually the case here. I applied my process in different lignocellulosic and lignocellulosic residues from different industries, and it was always working very nicely. Now we go to another topic, which is surface modification, and it is one of the very major areas in nanocellulose, but I will not be able to dig more into it for the time we have. But I want to give you a very fast idea for the fact that hydroxyl groups on the surface of nanocellulose, they can undergo so many reactions with so many different chemicals, and with that you can actually design whatever kind of nanocellulose surface you want. We are talking here about reactions like esterification, esterification, oxidation, carboxymethylation, cellulation, carbamation, amidation, and also you can actually graft polymers on the surface of nanocellulose. And with that, you can develop very functional nano-based cellulosic materials. When we come to the applications in general, I will cover some of them. It's impossible to cover all of them because there are more than 20 applications, and this is what makes even nanocellulose a very interesting material. The very first And the very most important application, which was actually the most interesting when the nanocellulose field started, is using nanocellulose as a reinforcement material to reinforce polymers. So if you check in the literature, nanocellulose has been used to reinforce biopolymers such as PLA, lignin starch, or synthetic polymers such as polyethylene and polyamides, and also for thermosets such as UF and PF resins. And this obviously has to do with the high mechanical properties and the low density of nanocellulose. And usually, many times, the aim also was to produce lightweight composites for certain applications. Here, I would like to give you some examples of the effectiveness of nanocellulose. And so here you can see the percentage of whiskers. These whiskers means nanocrystals. This is the old name of nanocrystals. So by putting a few percent of nanocellulose, and I would say here 20% is really a lot. So I'm talking about up to 5% is really like logical amount. With up to 5%, you can really get like improvement of 50 to 100% in like mechanical properties. And this is really, really like a big improvement. Now we come to automotive and aerospace industry, which are really interested in producing lightweight composites, which are actually recyclable and also mechanically strong. And this is really a special interest to car companies in general. And it has to do also with reducing the fuel usage. So in theory, if you are able to reduce the weight of a vehicle by around 10%, you are actually reducing 6 to 8% of fuel usage. And this is because of the location. Bio-based materials are replaced when they have pretty much low density with very decent mechanical properties, what make them really interesting for such kind of application. Here as an example of what's called nanocellulose vehicle, which was actually shown in a Tokyo Motor Show in 2019. This vehicle is many parts of it, obviously non-functional parts, are made of nanocellulose-based composites and also partly from wood. Nanocellulose is very interesting also for packaging industry because if you want to design biodegradable bottles and bags, nanocellulose is interesting. It improves the mechanical properties. And also nanocellulose mainly improves the barrier properties. We are talking about oxygen and water vapor improvement. And that's the case if you can see in the figure down, nanocellulose has a very special, very low oxygen permeability with a pretty much decent water vapor permeability. For tissue engineering and wound dressing, nanocellulose is also very interesting because it's biocompatible. We talk about mechanical integrity. Also, nanocellulose promotes cell regeneration. And let's not forget biodegradability. For example, if you make a nanocellulose-based material to replace some part of your bone, you would love this part of bone to be like hosting the calcification of your bone again through the pores of this nanocellulosic material, and then this nanocellulosic material will be actually biodegraded by time, and then you will have actually fully functional bone in the place of the nanocellulosic material. Nanocellulosic materials have been explored as artificial ligaments, heart valves, cornea, cartilages, bones, and also to replace blood vessels, and also very interesting for wound dressing. In pharmaceutical formulation, also nanocellulose is very interesting for people who work in the pharmaceutical industry. They know that different active ingredients have to be released in very different fashions in our bodies. For example, if you have headache and you want to have some like paracetamol, you would love this paracetamol to be released immediately. But while other medicines, they like have different release systems, they might be needed to be released in as doses or like delayed or targeted. And this is actually requires so much energy and time in pharmaceutical industry to optimize delivery systems for different active ingredients. And nanocellulose here is very interesting because it can act as a binder, improving mechanical properties of tablets. And there's a really direct relationship between tablet hardness and drug release. Also, nanocellulose can work as encapsulating agent. So the active ingredient can be encapsulated inside and then released at a certain time. And this was actually part of a work I've done like 10 years ago, where I made this special kind of nanocellulose. It's network nanocellulose, as you can see here in the photo. And I was able to encapsulate paracetamol inside. And depending on the amount of the nanocellulose, I was able to control the release time. See, with the small amounts of nanocellulose, we talk about 2% to 6%. I was able to control the release from 5 hours to 25 hours. And this makes such kind of material a universal excipient for many different active ingredients. Nanocellulose is also interesting for water purification due to the very high surface area and porosity, and also because nanocellulose can be functionalized with whatever kind of chelating agent you want, so you can make selective membranes to purify wood from certain contaminants. And here you can see in this figure how efficient cellulose nanofibers and cellulose nanocrystals without any modification in actually capturing copper compared to cellulose. But imagine after certain kind of functionalization, here we're talking about tempo oxidation and phosphorylation, the ability to capture copper actually improved like 2-3 times more. Here are examples of different functionalized nanocellulosic materials and how they were used to capture certain heavy metals in water. Also, nanocellulose, special nanocellulose forms are very interesting for cleaning up oil spillage, and we all know the environmental impact of oil spillage. We hear in the news this happening often, and you can actually synthesize certain kind of cellulosic materials which can actually recover oil from water without actually absorbing the water itself. And at the same time, these kind of sponges, they can float on the surface, so you can easily like just take them out. And obviously they can be reused like so many times. One application which is very interesting, especially for me also, is making electrically conductive composites. Many people will say, okay, but nanocellulose is not really conductive, and this is really true, but nanocellulose is very advantageous when it comes to this application. First of all, because of biodegradability. We all hear about the accumulating amounts of electronic waste. I heard the news just recently that in the last 5 years, there was an increase of at least 20% in electronic waste and the environmental impact it has. So nanocellulose being used as a substrate in electronics is really interesting and really advantageous to work with. Also, we talk about biocompatibility is a second advantage, especially if we talk about designing human health solutions. Nanocellulose is very also interesting, and let's not forget the mechanical flexibility of nanocellulose. So all of us expecting in the coming few years, electronics will be no more like inflexible. So motherboards, laptops, and mobiles, they will tend to be flexible. And I want to talk here about a certain application that I did myself in the last years. I actually developed a very interesting nanocellulose material, which looks like a nanowire, by making a core shell nanostructure, which is really conductive with a very, very decent conductivity. And such kind of nanocellulose is actually especially interesting for so many applications in terms of sensing and in terms of 2D and 3D printed circuits. So this is a summary of the projects and applications I worked on in the last like 11 years, just to give you an idea. This is like the major projects I worked on, and you can see there are like many applications maybe I didn't even cover here. And no one person can be really expert in all these applications, obviously. So it's really a big field, a big area, and mainly people tend to be specialized in a certain application. So in summary, I would like to say nanocellulose has obviously a great potential in a wide range of applications. Most of the work in the literature has not been scaled up, and this is not surprising, but I expect more products will be available in the market soon. Obviously, nanocellulose is also limited by its price, especially if we talk, for example, in packaging industry. Why would I put an expensive material in a packaging material? So sometimes it's not really feasible, but it's really expected that the price will significantly drop, which actually what's happening these days by the introduction of more products in the market. But it's a personal recommendation that nanocellulose is more cost effective in high value applications such as medical applications and electronics, and obviously also in automotive industry. That's all from my side. I hope I was able to give you a very small tour in the nanocellulose world, which is really huge. And if you feel to contact me later, this is my personal email in case you don't have the chance to ask me. And thank you very much for listening.
Thank you, Dr. Abushammala. Thank you a lot. That was a very impressive speech. And now, okay, I'm sorry. I will open my. So for the question part, we will also leave these questions at the roundtable discussion part. Now, let me welcome the next speakers. Our next speaker is Dr. Niklas Garoff, the Business Development Manager at Stora Enso. Dr. Garoff has a MSc in chemical engineering and a PhD in paper technology from the Royal Institute of Technology at Stockholm. After his PhD, Dr. Garoff was recruited to Stora Enso, a leading producer of wood fiber-based packaging materials, pump, wood-based constructions materials, and printing paper. In 2012, Dr. Garoff initiated a project aimed at developing a new carbon fiber from wood-based raw materials that now is one of Stora Enso's top strategic projects. Stora Enso is today leading the development of the bio-based carbon fiber. The topic of his speech is carbon fiber from renewable raw materials. Let's welcome Niklas, Dr. Niklas Garoff. Hello, Dr. Niklas Garoff. Hello, Dr.
Yes,
Garoff. Can you
hello.
hear us?
Can you hear me?
Yes.
Excellent. Very good. Very good. Thank you very much for this kind introduction. It's a great pleasure for me to give a speech at the Carbon Tech Live webinar on green composites. I have prepared this presentation together with my co-author, Dr. Kurt Uehlein, who is Chief Marketing Officer at the rayon company Cordenka. And I'm going to talk about carbon fiber from renewable raw materials. So, I will cover the following topics in this presentation. First, I will briefly introduce the two companies, Stora Enso and Cordenka, respectively. And then I will give you a brief introduction to the carbon fiber technology developed by Stora Enso. And explain to you our value proposition and the expected performance that we believe we can achieve at a commercial scale based on our recent findings from the research project. Then I will continue with explaining the drivers for decreasing greenhouse gas emission levels. And then as a last exercise, I will demonstrate the effect of using carbon fiber in a product, in this case a wind energy rotor blade, and show to you the negative impact that carbon fiber, as it is used today, has on the carbon footprint of this particular rotor blade. And I will then conclude this presentation with some final remarks. So, a brief introduction to Stora Enso and Cordenka. At Stora Enso, it all starts in the forest. We are a major producer of different fiber-based packaging grades and construction wood and printing papers. And our primary raw material is the tree coming from the forests. They come from our own forests in Sweden, from private forest owners in Scandinavia, or from our eucalypt plantations that we have in Latin America. And for every tree that is harvested, we are replanting at least 2 trees. Scandinavia has never had more forest than in these modern times, and it is because of the industrial forest industry. We believe at Stora Enso that the world needs a new approach to materials. We have to leave our present world based on fossil materials, finite resources, generating carbon emissions and waste. And we have to move towards a world where we use more renewable materials that are recyclable, biodegradable, in the business where you can store carbon to reduce the carbon and greenhouse gas emissions to the atmosphere. And how do we do this today at Stora Enso? Well, we have 6 different divisions producing different fiber-based products. In the packaging materials division, Stora Enso is producing different fiber-based packagings for the food markets, beverage market, and graphical boards, and also corrugated boards. And in the packaging solutions division, this is aimed at designing new kind of packages together with customers. In the biomaterials division, Stora Enso is producing a large variety of different pulp grades, cellulose, for making fiber-based packaging, printing papers. We are also producing specialty pulps, such as dissolving pulp for the textile industry and fluff for the hygiene sector. Then we have the wood products division. Here we are producing basic wood materials and also quite sophisticated engineering wood-based construction elements for the construction market. And then we have our printing paper division. Here Stora Enso is producing different grades of printing papers. This is a declining business, so printing paper markets are declining by 3 to 4% every year. So Stora Enso is actively decreasing its exposure in these shrinking printing paper businesses, and aims at growing in the additional businesses, packaging materials, and so forth. And what is quite new at Stora Enso is that we have again an own forest division where we are managing our forests in Scandinavia. Very briefly, some numbers. So Stora Enso is a quite large company. We have a turnover of about 10 billion euros. Most of our sales is generated in Europe, followed by Asia Pacific. China is actually our most important market in the Asian region. Currently, we have there are 26,000 employees working at Stora Enso in more than 30 countries. Most of them work in Finland and Sweden. But then we have followed by China actually. So we have a lot of personnel working in China. In the Beihai region in Guangxi province, we have a liquid packaging board mill that was started a couple of years ago to serve the Chinese markets. One slide about Codenka. Codenka is a medium-sized company placed in Germany. They have a turnover of about 170 million euros. And they are the leading producer of rayon fiber with a 55% global market share and 32,000 tons of fiber capacity. Their rayon yarn is used for producing tire cords in ultra-high performance tires, hoses, and some composites. It has also been used as the precursor fiber for carbon fiber production, but in this case, it's not for structural carbon fiber, but for thermal applications. And as in the case for Stora Enso, their raw material is 100% coming from the forest. So that's a big common thing that's a big thing that we have in common, Stora Enso and Codenka. So carbon fiber development at Stora Enso. This is a project that I initiated about 8 years ago, and what started as a basic research project is now morphing into a pilot stage, coming closer to a business. And what we have demonstrated at laboratory scale is that it is possible to produce a high-performance carbon fiber from wood-based raw materials. In this case, cellulose and lignin, which are the two largest components in the tree, material components. And our present R&D results indicate that we can achieve performance levels that are in the range of standard modulus and high modulus carbon fibers. The process is scalable because it is based on unit operations that are employed today by different industries, as I will explain to you in the following slide. And now Stora Enso is upscaling the process from lab scale to pilot scale, together with industrial experts along the value chain. And on this picture, you can see some examples of lab scale products. To the left, a precursor reel, 1,000 filaments, and then a stabilized fiber from that precursor, and a carbon fiber with the sizing. Our value proposition is a neofiber, a new kind of carbon fiber with a high performance at a competitive price, at a low carbon footprint, and based on renewable raw materials. We are ready to serve markets wherever we can qualify our fiber. It will be mostly in industrial segments like wind energy, automotive, also construction markets is very interesting to us, and sporting goods, and perhaps even secondary structures in airplanes. So how do we do this? Let me first explain how carbon fiber is made today. If you look at the lower part of this picture, it shows the process scheme of today's carbon fiber production. 98% of all carbon fiber is made from an oil-based raw material called polyacrylic nitrile, PAN. Starting from the oil, propylene is obtained in the steam crackers. This propylene is then converted to ACN, acrylic nitrile monomer. And this is the main building block for making the precursor. The ACN is then co-polymerized together with other co-monomers to give the PAN polymer, the polyacrylic nitrile polymer. And this is then dissolved in different solvents such as DMSO or DMF to give the spinning dope. And this spinning dope is then spun to a precursor using wet spinning or air gap spinning. And what you get is a white reel, as you can see in this bottom picture. And this precursor reel is then thermally converted to carbon fiber by feeding it to different furnaces at different temperature zones and different residence times. The first furnace is a stabilization furnace, where the precursor is converted from a thermoplastic material to the thermoset material. And then what follows is low temperature and high temperature carbonization. And finally, a sizing is applied, and then the carbon fiber is spooled and packaged. So, and 98% of all carbon fibers today are made according to this process. Well, Stora Enso has a different approach. We start from the tree. From the tree, we obtain cellulose and lignin. The cellulose is converted to viscose. The viscose is then dissolved in caustic soda. And lignin is added to this mixture. And this is how the spinning dope is created. And this spinning dope can then be wet spun to a precursor. In our case, it's a brownish golden looking precursor reel. And this precursor is spun in a similar method as viscose fibers are spun today. The precursor reel is then subjected to thermal treatments in stabilization and carbonization to give our neofiber, our novel carbon fiber. So you can see that practically industrial unit operations are being used for making the precursor and the carbon fiber. Now, this slide shows the tensile strength and tensile modulus of commercial carbon fibers. Carbon fibers can be grouped into 3 different families, depending on what performance they deliver. The biggest group is standard modulus carbon fiber, which have a modulus between 230 270 gigapascal, and a tensile strength of between 3 to about 5.5 gigapascal. And this corresponds to about 70% of all carbon fibers are in this standard modulus regime. And these are the carbon fibers that are being used for industrial applications such as rotor blades, automotive, construction. Then we have another group called intermediate modulus fibers. These have much higher tensile strength and somewhat higher modulus. This is the high-priced carbon fiber that is used for primary structures in airspace, in airplanes, such as wings. And then we have another group called high modulus carbon fibers. These have moduli between 340 up to more than 600 actually. A bit lower tensile strength, and these are used for applications where you need very, very high stiffness, for example, robotic arms. Now, based on our lab scale results, we expect that our neofiber at commercial scale will have properties that are shown, indicated in this green region. So we have actually already produced carbon fibers with the moduli up to 500 gigapascal. And what we are now doing is that we are upscaling this process using more sophisticated equipment, and thereby we will reduce the defects in the fiber and increase the tensile strength. So we are quite confident that we will be able to produce good standard modulus carbon fiber. Based on these results and based on the very positive feedback that we have received from major users of carbon fiber today, we are now upscaling this process together with partners. The spinning of the precursor is being carried out at Kodenka, the leading supplier of high-performance industrial rayon. A joint development agreement was signed in March this year, and this cooperation was announced in a press release in early May this year. The thermal conversion of the precursor to carbon fiber takes place at the Institute of Lightweight Engineering and Polymer Technology, ILK, at the Technical University of Dresden. And the objective of this present pilot phase is to have a throughput of about 20 kilos of high-performance carbon fiber for first material qualification tests. And this is to show you the progress we have made in just 2 months actually at Kodenka. On the left-hand side, you can see a precursor reel at lab scale. So this is what we've been doing for the last couple of years. And on the right-hand side, you can see a 3K precursor reel coming from Kodenka. You see the magnitude of production has been multiplied by a factor of 10 to 100. So this cooperation is running very well. But why are we doing this? Why is it important to have a carbon fiber with a low carbon footprint? Well, there are strong drivers for decreasing greenhouse gas emission levels. If you look at the European Union, they launched an ambitious climate program, the 2030 Climate and Energy Framework. And this is the contribution of the European Union to the Paris Agreement, which is aimed at keeping the temperature increase below 1.5 degrees. This means that at least 40% of the greenhouse gas emissions must be cut by 2030 compared to 1990 levels. And the member states are required to adopt national energy and climate plans for the period 2021-2030. For the companies, this means that the EU has set a total limit of greenhouse gas emissions, and the companies are required to monitor and report these emissions. There's a fixed number of allowances that are issued for each company per year, and each large company must have enough of these allowances to cover their emissions. Otherwise, they will face significant penalties. What they can do is to trade carbon dioxide certificates. A company can, for example, buy certificates from another company to cover their allowances. But this is actually not the main driver for in the business. It is So before going to that topic, I just show you this graph. It shows the development of the CO2 equivalent emission levels in the EU, starting at 1990 from about 5.7 billion tons of carbon dioxide equivalents to right now we are about 4.4 billion tons. So the EU is well at target to reduce the carbon emissions by 20%. But then for the coming decade and coming decades, the ambition level is even stricter. So the target for 2030 is to reduce this by 40%, and by 2050 by between 80 and 95%. So the companies are having will face tighter regulations to cut their greenhouse gas emission levels even further. What's even more interesting is that climate change is fundamentally reshaping the world of finance, because investors have realized that climate change makes the world more unpredictable. And this is bad news for investors, because investors must be able to predict the future somewhat accurately to estimate if an investment is profitable or not. And now questions arise such as, can cities afford infrastructure needs as the climate risk reshapes the market for municipal bonds? What will happen to long-term mortgage, which is a key building block of finance, if the lenders, for example banks, cannot estimate the impact of climate risk over such a long timeline? And what happens to inflation and interest rates if the cost of food climbs from drought and flooding? Investors have understood that climate risk is investment risk. And this has led to a reassessment of risk and asset values. Now it's not only about making money. Sustainability has become an important part in the portfolio management and risk management. And these lines are actually taken from the website of BlackRock, the largest institutional investor in the world. So you can take a look at that. What does it mean for carbon fiber? Well, it's bad news, because carbon fiber has a high carbon footprint, and this I will show you on this example case, which was done together with the UK-based engineering and consulting company Struck team. It's a case where we estimated the carbon footprint of a wind energy rotor blade that uses carbon fiber in the so-called spar caps, compared to a rotor blade using glass fiber in the spar caps. And this was a cradle-to-gate analysis. Let's first take a look how a wind energy rotor blade looks like. It's practically hollow. The skin is made of a composite of glass fiber and a polymer. The skin is stabilized through a spar cap, and this can be made from either glass fiber composite or carbon fiber composite. And then you have these vertical shear webs that are these distance holders between the two edges of the rotor blade. So the spar caps, they can be made from either glass fiber or carbon fiber. Carbon fiber has a big advantage over glass fiber, because it increases the stiffness of the blade, which makes it possible to design larger blades that are even lighter and are thinner, giving a better aerodynamic design. And this in turn makes it possible to either produce more energy per windmill or decreasing the cost of energy. So using carbon fibers in the spar caps has big advantages. And actually 20% of all carbon fiber demand goes for this specific application. It's a huge market. So it's about 15 to 20,000 tons of carbon fiber goes for this particular application. So, but there's a problem, and that's the carbon footprint of carbon fiber. In this table, you can see the carbon footprint of carbon fiber compared to other construction materials, and you can see that the carbon fiber has a footprint of about 30, meaning that for the production of 1 kilo of carbon fiber, about 30 kilos of carbon dioxide equivalents are being emitted. And this is much, much higher than the CO2 footprint of other materials. Glass fiber at 1.5, stainless steel about 2, depending on the recycling rate. Aluminum about 15. And how does this high carbon footprint impact the rotor blade? Well, we did a study in the Struck team, and here we compared 2 different rotor blades, one that is using glass fiber for the spark hubs and one that is using carbon fiber in the spark hubs. And what we observed was that if you use carbon fiber in the spark hubs, the blade weight decreases from 35 to 30 tons, which is good. But the carbon footprint increased by 35% from about 170 tons to close to 250 tons of carbon dioxide equivalents for an 80-meter rotor blade. So that's a problem, and that's only one example showing that even small amounts of carbon fiber may have a significant negative effect on the carbon footprint of your product. So what are the conclusions? There's a global trend towards tighter mandatory carbon dioxide reduction to achieve the goals of the Paris Agreement. And investors have recognized that climate risk means investment risks. And sustainability has become an important ingredient in the portfolio and risk management for investors. Today's carbon fiber has a very high carbon footprint compared to other construction materials, and this may significantly increase the carbon footprint of the final product. Now, Stora Enso is developing neofiber, a novel carbon fiber with a low carbon footprint, together with industrial partners. And the joint development project with Cordenka is an important step into that direction. Thank you very much for your attention. For more information, please contact me, preferably by my email address. Thank you very much.
Thank you, Dr. Garoff. It was a wonderful speech. So, dear audience, if you have any questions for Dr. Garoff, please raise your hand at the roundtable discussion round. We will help you to open your microphone to speak with Dr. Garoff. Now, please welcome our last speaker, Dr. Mårtensson. He is the CSO at Bcomp. Dr. Mårtensson, PhD in Automotive Composites Structure from Royal Institute of Technology, KTH, Stockholm, Sweden. Dr. Mårtensson has previously worked as a strategic expert at Volvo Car and has over 15 years of experience in the composite industry. The topic of his speech is Bcomp brings high-performance, sustainable solutions to the automotive industry. Let's welcome Dr. Mårtensson. Hello, Dr. Mårtensson.
Hello, thank you very much for that introduction. I hope you hear me okay.
Yes, so could you also open your camera that we can see you there?
Yes, of course I will. So I have to allow. So, hi, nice to meet you.
Hi, nice to meet you.
So, first of all, thank you very much for organizing this webinar. In the times of restricted traveling, this is a fantastic way to reach out to new customers and new markets. So, thanks a lot for that one. As presented, I will talk about how to bring sustainable high performance into the automotive industry. And actually, I know Niklas, Dr. Niklas Garoff very well personally, and I follow his project with immense interest. So I will, of course, talk about where you need the right material in the right place and where you actually can substitute carbon fibers and other less environmentally good materials with sustainable solutions. So Bcomp is a high-tech startup from Switzerland, and I'm trying to see here. And we are working on bringing lightweight, high-performance, sustainable solutions into different kind of sectors. And what is very clear looking at the natural fibers of the world today is that they are very performant. You just need to do some engineering and find solutions how to deal with them. And our patented solutions today can actually provide, compared to the state-of-the-art solution, up to 50% weight reduction looking at automotive interiors. We can be 30% more cost-effective with the same performance as carbon fiber composites in body parts for cars, and reach up to 75% lower eco footprint compared to carbon fibers. And that I will talk about, and I will talk about how we can succeed with that and what's special with the solutions from Bcomp. So Bcomp, we're working on 3 different silos with our products. We work in sports and leisure, where we have a lot of weight benefits and a lot lower eco footprint. And then we work on the motorsport and the supercar side, where we can be much more cost effective in a lot of parts, and also have a lot of lowering the eco footprint drastically, but without jeopardizing this performance side, because carbon fiber is a fantastic material. And in the large scale automotive side, we are actually targeting to replace injection molding interiors, but also these NFPP interiors that are the most sustainable ones you can find out there. And even compared to those, we can reduce the weight with 50% and have a 50% lower eco footprint. And I don't go into details, but I think we can, in a normal car interior, we can decrease the plastic content with over 70%. So how is this possible with the natural fiber composites? Everything is based on the underlying magic. So what Bcomp has done is that we have developed something called power ribs, and it's a natural fiber sustainable grid structure that you can apply on the backside of composite structures. So typically working with monolithic laminates, we can outperform most of the given materials today and provide as stiff structures as a lot of carbon fibers can do, but in a much more sustainable way and actually much more cost-effective way. And this is possible by pure geometrics of a part and increasing the thickness of the part without increasing the weight. And so it allows us to be extremely performant and still have a very low weight and high stiffness. But I once again emphasize on the thing, you have to work with the right material in the right place. There are multiple areas where other materials are much more performant. So we target very much thin-walled structures that are stiffness designed. So looking at how we use this, I will focus not on sport and leisure today. I will talk about motorsport and large-scale mobility. So looking first at motorsport, which is a very classical composite industry. So here we actually take the power ribs and then we apply it on the backside of a laminate to increase the stiffness and reduce the material content. And here we can either work with our laminates, the Amplitex fabrics, and put the power ribs on the back, but we can actually combine it also with carbon fiber, just reducing the amount of carbon fiber going into a part. And there we actually outperform carbon fiber solutions. So we become lighter, stiffer, and a lower cost. And these applications are today used in various amount of racing series already. And what they see now is that since we're using a sustainable material, we can be much more cost effective. They can buy in on this circular economy where you actually start to looking at the whole, not only cradle to grave, but also cradle to cradle, what's actually happening with the energy that you put into material. And we have for such a long time in the world worked with linear materials where you cannot actually find a second life. So you can recycle it, you can put even more energy in it because most of the recycling aspects demand energy demanding recycling operation. But here you can actually recuperate the energy that is put into the fiber while growing. You can use that energy again. You can allow new fibers to grow and you can rework them again. So equal performance, our fabrics, our solutions, thanks to the power ribs, is actually behaving much safer in crash situations. So we don't have this chaotic failure where you have explosions and debris all over the racetrack. And as I said, more cost effective, so it allows more people to actually be a part of this racing industry. And this we are now taking into the supercars of this world, and we are seeing a huge interest to bring this also to the road market for body parts. So this is typically how it looks. You apply 1 or 2 layers of our Amplitex fabrics, and then you put the power ribs on the back. So we have very high performance, low environmental footprint, improved safety, and also improved cost efficiency. And we are today racing in more than 16 racing series, and moving fast into the most high performance and faster ones. So that you will see in the future that will come, so to say. And we have won multiple awards in the automotive sport and motorsport region. So looking at what's actually happening, the previous speaker touched on this, but actually what is quite immense, I worked with carbon fibers for over 15 years, and I had no clue that you actually use a lot of water in that. So everything from water, CO2 footprint, and energy required during production is reduced by using natural fibers. And then typically something, I always use this comparison by building house out of either concrete or wood. So you consume a huge amount of energy building something and you can never recuperate it, never do anything with it when it's out of use, or you can build it out of wood, a building, and then you actually store CO2 in the structure, so it becomes a CO2 trap. And then when it either you have to tear it down or wherever, you can recuperate that in energy, and you can regrow new trees. And this natural fiber composites has exactly the same approach. So the structures that you have in your car in the future, or interiors of airplanes, or so on and so forth, can actually, the day that you do not want to use it, you can recuperate that energy and use it again, so to say. So looking at what will happen then in the large scale mobility sector with our applications, we once again use the power ribs on the back, but in this application we use a much more low performance but with completely sustainable substrate called NFPP. So this is already used for 40 years in the automotive interior. But what we do is that we can take away more or less 60% of that material, apply the power ribs on the back, which has exactly the same material constitution. And then we can have the same performance and stiffness. We have a much lighter vehicle with a much lower environmental footprint, and we reduce a large amount of plastic in each and every part. And actually, even here, we see that when we apply this in door panels and so on, we have a much better crash behavior because we do not have penetration of sharp objects into the passenger area and so on. And this is now, we have a very tight collaboration with the Volvo car group company, Polestar, their electrical vehicle champion, where we design the whole future interior of their vehicle, where we talk about reducing weight, plastic, and lower the footprint of the complete interior. So it's extremely interesting case, and we're putting that into production now. And what was key for us to go into the automotive industry was that we had a process that was not influencing the present processes used. So we have less than 60-second compression molding process. So we can have power ribs on the back. We can even back injection attachment points and so on. So we actually do not change at all the supply chain what they use today, because the automotive industry is extremely reluctant to change. It's very cost driven. So we could not come with something that was much more expensive. So we bring all these benefits, and it for more or less the same price without big changes to the supply chain. And I mean, looking at it, everybody thinks, oh, but what can you actually gain on lowering the weight of an interior? I mean, we talk about 30-40 kilos we can win here. And if somebody would say that without major cost impact, lower 30-40% of the vehicle weight in the body parts, that is more or less impossible. So this also once again comes back to the thinking that you have to use the right material, but even more the right solution in the right place. And this is the way forward for the future, for the mobility revolution that we're seeing happening today. So we can apply in these parts. We have the whole door panels, we have the seat backs, and everything is actually our materials, either with our visual fabrics, like on the seat backs, the black areas, or covered with leather on all the other parts. So this is a great collaboration with Polestar that is going to be produced, and their home country is actually China. So you will probably be the first ones who are driving these cars, and which makes me very happy. So looking at what's actually starting to be communicated out in the industry, I take Porsche as an example, where we collaborate on the GT4. So what Porsche does now is that they actually starting, this is probably one of the companies that you most relate to carbon fiber and synthetic materials and really high performance approach and so on. So for them, we have produced the whole door structure, inner and outer, rear wing, front bumper, rear bumper, and they actually communicate this. So they talk about that this sustainability movement is actually happening now, and we have to be conscious about our future and how we actually impact it. So for us, it's a very, very clear sign where the industry is moving and what needs to be done, so to say. So this is just a small, short introduction of what's happening at Bcomp, of different awards we have won in the last couple of years. But we are not stopping now. So we are in the lead of how to apply natural fiber composite, and we will stay there. So by that, I would say thank you, and I'm very happy to take any other questions or launch into the discussions about a greener automotive industry. Thanks a lot.
Thank you, Dr. Mårtensson. Thank you a lot. So yeah, that was a very wonderful speech. So yeah, here I offer the presentation today. So dear audience, if you have any questions, wanted to speak with the speakers, you can click the hand button. We will invite you to the front page to talk with the speakers directly. Thank you. So yeah, we see Danish, Mr. Danish raised a hand. Danish, we will help you to open your microphone. Okay. Hello, Mr. Danish, can you hear us?
Yes. Can you hear me?
Yes. Wait a sec. Dr. Mårtensson, Dr. Garoff, and Dr. Abushammala, and Dr. L. Could you please open your camera?
Yes.
Okay, great. Dr. Aid, could you please, use your cell phone for the round discussion part? Dr. Aid. Okay, fine. So, hello, Mr. Danish.
Yes.
Yeah.
So first of all, I'm from China, Kobe University, and I am the PhD scholar in Material Science School. So I'm very happy, and I'm very motivated to learn and to hear this amazing webinar. And Dr. Alaa, Dr. Abushammala, everyone is a great. So my question is, my research is regarding photothermal materials. So photothermal based materials for water desalination. So I use some cellulose and some nanocellulose. But the matter of fact is that whenever I used and as a thin films using PLD, or so at PLD operate on greater than 300 Celsius. So my concern was that, is there any method I dope some nanocellulose into metal oxide and to coat a nano size thin film on flexible substrate? Please.
I believe this question is for me. So is it?
Yes.
Yes. What temperature was it? 800 or 300?
300.
300.
Yes, greater than 300, almost.
Yeah. The temperature for sure is high for nanocellulose. I would say like unmodified nanocellulose degrades earlier than this, or at least it starts to degrade earlier than this.
Yes.
So that would be an issue, but that can be solved by doing like one of two things. Sometimes surface modification increases the thermal stability of nanocellulose, because most of the thermal decomposition of nanocellulose happens through the hydroxyl groups. So certain chemical modifications might help you with this, but that won't go like above 300, 350. So cellulose itself.
Exactly, because I want to deposit nano, because ALD or PLD can help us to deposit nano. If I use brush or something like other methods, but the thickness couldn't be achieved. So my concern was that I want to add some antibacterial films.
Yeah.
So Dr. Alaa also in his speech say some copper or Ag based some films. So my question was that, is there any suggestion if I didn't use PLD, ALD, but I use cellulose, lignocellulose or nanocellulose and use some metal oxides, is there any other technique to deposit thin film?
Like if you want to talk about it in general, this is like a very different topic. Did you try like a spin coating in general or such kind of technique?
The point is that my substrate is flexible, just like foam, and it cannot place on the spin coating stage. So
okay. You know what I would recommend you? Maybe if you write me more details about this issue, send it to me by email. So just to save the time here, maybe you can send me the email, your question with all the details, and maybe I can really support you with finding a solution.
Okay. I have a last question from all. So how we can know about the bonding between cellulose and metal oxide nanoparticles?
Like chemical bonding?
Yes, chemical bonding, because the chemical stability of composite.
I mean, if like we want to say just really roughly for now, we can talk easily about FTIR, you know?
Okay, FTIR.
Yeah, so, if we want to talk about it just really fast.
So in my group, somebody used some binder to join cellulose and metal oxide nanoparticles. So is there any technique to dope some cellulose into metal oxide nanoparticle and make a stable composite?
Oh, that depends on so many factors, you know, like that's it's really general to answer, because it depends on many things. Where your metal oxide are actually placed, they are in a certain, what kind of solvent, are you using actually solvent for that? Is it organic, water, it's a mix? So that's why I think if you send me like your exact question with all the details, because the answer will be always different based on the scenario, you know?
Okay. So thank you so much.
If you send me the procedures exactly, I can really support you in this way better, I think.
Thank you so much, sir. Thank you so much. And I'm very pleased to hear you. And how I can say as a Muslim, fi amanillah.
Salam.
Okay, sir. Evallah.
Hello, Danish.
Thank you so much, ma'am. Thank you so much, ma'am, for giving me a chance.
Yeah, Danish, I found out that you also have a question for Dr. Alaa.
Exactly.
Right?
Exactly.
Okay.
Yes. Dr. Alaa, can you hear me, sir?
Yes, I hear you.
Assalamu alaikum, sir.
Wait a second, I will help Dr. Alaa open his microphone.
Hello.
Assalamu alaikum, sir.
Wa alaikum assalam wa rahmatullah.
Sir, how are you? Fine, sir?
Fine, alhamdulillah. What's
Sir,
your question?
Sir, I'm truly fine, alhamdulillah. I have a question regarding, as you mentioned in your presentation, about Ag and copper antibacterial films. So how you deposit these films, and how you fabricate these films?
How to fabricate nanosilver and nanocopper.
Nanocopper. Okay, sir.
Okay.
So which
you can
technique?
Send me email. I will send you the procedure, inshallah.
Okay, sir. Okay, sir. Thank you so much, sir. Thank you so much.
Thank you. I will come.
Thank you, sir. Okay, sir.
Danish, do you have any more questions?
Yeah, no. Thank you so much, ma'am. Thank you so much.
Okay, thank you, Danish. And we found Mr. Kashawani raised a hand. I will help you to open your microphone.
Hi, good afternoon, everybody. Assalamu alaikum. This is Ghanem Kashwani from NYU Abu Dhabi. I have a couple of questions for the whole panels, if it is possible, please.
You talk about cement panels.
Yeah, please, Dr. Alaa, my question is that sometimes we try to use the cellulose fibers from the palm, and especially that food waste is huge in Arab world. So we try to utilize that. However, the main challenge that high alkalinity in the cement matrix is affecting the durability. So still people in the commercial aspect, they use synthetic fibers. So any suggestion, rather than a treatment, that we can enhance the durability performance with the fibers inside the cement matrix? And a general question also for Dr. Hatem, if I can ask, about the nanocellulose, that is it possible, since now people are using nano tube for the carbon, can we do some mix between nanocellulose and nanocarbon? Because nanocarbon, one of the challenges that it is the flexibility to manufacture and to handle it. So if we mix these two, can we quote unquote enhance their agility and their viscosity to have more commercial aspects? Thanks all, and this is all my question.
You are welcome. About your question, first question is how to improve the compatibility between natural fiber and cement composite. I understand, right?
Yes, doctor, please, yeah.
Yeah. The problem is the alkalinity or acidity.
The alkalinity in the so usually in the cement matrix we have high pH because we don't want the reinforced to get corroded. So we try to keep the pH high.
High pH, it's mean acidic or alkaline?
So we don't want the pH to go down so that we protect our reinforcement steel.
It's there is some type of modification of the fiber to overcome this problem. I can send you it. Please send me email and I send you this kind of modification.
Okay, thank you. I will do that. I'll share my email with the panelist with you now. My second question.
Yes.
Maybe I can. Tfadal, Doctor.
Yeah, sorry. Maybe I can also contribute in this question regarding the alkalinity of concrete. Overall, you need to build a protective shell around your cellulose fiber. This applies also to nanocellulose. If you build a hydrophobic shell around your cellulose or nanocellulose, this way you will actually you will not allow the alkalis to go inside the fibers, and with that you actually kind of protect them. This is actually a work I've done also with other colleagues in the last years, and this is one of the approaches. So you don't, in a way, they don't allow the the ions to go around and through the fibers and destroy them.
Dr. Hatem, is it possible to share if you have any publication in this regard with the hydrofabric shell? Is it possible to share it with us?
Yeah, sure. You contact me, my email, I can really share with you I have this already done.
Yeah, I'll try to get your email. I shared my email with all panelists. I don't know if it is visible. It's gaka289@NYU. So if I have your email, it will be my pleasure to read this publication.
Okay, thank you very much. And for the making composites out of carbon nanotubes and nanocellulose, this is actually also a work which is done and interesting to so many people. As long as you aim at certain properties, you can pretty much use whatever material is available and useful for you, and considering so many factors like cost and environmental impact. So that's not really a problem. It's really possible. And I know actually some colleagues who are doing this work. So it is possible, yes.
Thanks a lot, Dr. Hatem, and Dr. Alaa, thanks a lot for your time.
Regarding the use of carbon nanotube and CNC or CNF, the effect here is a summation. So you can use any material, and the effect will be the combination of the properties of all additives which you use.
Thanks a lot, Dr. Alaa, for your nice response. Thank you.
Welcome.
Thank you, Mr. Kashwani. And we found out that Christian raised a hand. Christian, I will help you to open your microphone. Christian? Yes. 你们先不要动，我来讲。
Can you hear me now?
Yes.
Yes.
Yes, perfect. I have a question for Niklas. Thanks a lot for the highly impressive presentation about lignin-based carbon fiber. I have a question about the carbon dioxide footprint comparison.
Yes.
What are the energy you use to produce the carbon fiber for the plant-based and the lignin fiber? I'm pretty sure having a renewable resource for the highly energy-consuming process would affect that carbon dioxide footprint enormously.
Yes. Hi, Christian. Nice to hear your voice again. You are absolutely you are absolutely right. The carbon footprint of any carbon fiber is the largest impact is the electricity mix for the thermal conversion, and how this looks like in the region, whether it's based on nuclear energy or coal or oil. And a palm-based carbon fiber producer can reduce the footprint radically by using, for example, hydropower, such as SGL is doing at the Moses Lake facility. And the figure that you saw in the presentation, 30, is based on a number that we got from ELG, this company that is looking at the recycling of carbon fiber. And this was also cross-checked by other consultants, and this is based on a power mix, a typical European power mix, with some nuclear, coal, oil, and what we aim at. So we have not published any carbon footprint for our carbon fiber yet. So this is yet to come. And what we are aiming at is to produce carbon fiber in region with such as Sweden or Norway, with a very high share of hydropower, nuclear, and very low share of any fossil-based energy carrier. So, and on top of that, we will also benefit from carbon credits coming from the precursor, because based on the fact that the precursor is made from free-based raw materials. And so this will be even an additional benefit to our carbon footprint. I hope this answers your question.
Yeah, thank you very much. And I see, especially for wind energy, it will be a big challenge for the next decades, the recycling of the rotor blades. And I think a very good point is not to use oil-based carbon fiber, but to start with the bio-based carbon fiber, and maybe with the bio-based resin in the future. I think this will help a lot to have a less lower carbon dioxide carbon footprint for the whole composite industry.
Yes,
thank you very much.
Agree. Thank you, Christian.
Christian, any more questions?
Not so far, thank you.
Okay, thank you, Christian. So, any more questions? If you have any questions, please raise your hand. Please raise your hand. Click the hand button. Any questions? Haki, Mr. Haki, do you have any questions? Yeah, if you have questions, please raise your hand. Okay. Okay, fine. Greg, I will help you to open your microphone.
Okay.
Okay. You can hear you. Mm-hmm.
Yeah. My question is, who is considered a leader in molding composite structures? Did you hear me?
Well,
yes, we are back.
Who or what sector is considered the leader in molding composite structures along what we've been talking about tonight with green composites?
What?
I think, are you aiming for what
someone to talk to?
Demanded any new processes or so? Because at least for our materials and this is per Mårtensson Bcomp. So for our materials and our solutions, we are actually working with exactly standard. So either for high volume composite, we are working with the standard automotive processes out there, and also for normal composite. So it's not a revolution. You don't have to. It's not rocket science to start using these natural fiber composites. It's really extremely straightforward, and that is shown by all the customers we have also.
All right. Can I just send my email on Q&A or chat and get some of you to follow up with me afterwards?
Yes, absolutely.
Thank you.
Thank you, Greg. Do you have any more questions? All right. So,
no, that's it.
Okay. Thank you. So, Dr. Eunice, do you have any questions? Dr. Eunice, if you would like to speak with the speakers, could you please click the hand button that we would help you to open your microphone? And Dr. Shahab. And any questions? So, so I will share questions at the Q&A part. So, the question is, Dr. Alaa, thanks for the very interesting presentation. Could you elaborate on the medical applications of the green composites?
I think my friend Dr. Hatem talked about this. This is great work on the application of green composites in medical applications. There are some medical for detection of some disease like cancer, and some targeting drug delivery. And all these applications up till now in the lab and pilot scales. Up till now, there is no real application. No, some application only on the diagnostic of this disease. I have other question come from somebody. Is NFPC worked in high temperature applications? Unfortunately, this is green composite. The durability of green composite, it's only from high temperature. It depends on the polymer which we use. For example, if we use polyamide or any other engineering plastics, it can undergo more than from 60 to 70 degrees. So it can, for example, work it in Gulf area or any other countries, hot countries. The temperature of processing of such polymers or of such composites we work on after more than 200 centigrades because after that temperature, the natural fiber start to do degradation and thermal degradation. So this is the limitation of such composite. Another question about the effect of nano silver on the health. Nano silver is the effect is under study. We now didn't have any data, so we need to make some migration tests to detect the percent of migration and the effect of these particles on the health of people. But in the literatures and many publications, it's said that silver and copper is safe for human beings. Any other questions?
Okay, Doctor. Thank you, Dr. Ali. And I think this is another question for you. That is, do antibacterial used in the film have some side effects for the safety of the food? Do you have any data to support for your ideas? Thank you.
I already answered this question.
Okay. All right. Okay. So, do you have any questions for the other speakers?
Thank you.
All right. So, Dr. Garoff, do you have questions for the other speakers?
I didn't know that carbon fiber also consumes so much water. That was new to me, Per.
I mean, that was new to me also. I mean, I as I said, I worked 15 years with it, and it. So all the data I presented in my presentation is actually not made by us. It's made by the European Space ESA. Yeah. So it's very official data. So it's I was very surprised.
Okay. No further questions from my side.
Okay, Dr. Mårtensson, do you have questions for the other speakers?
No, maybe actually to Dr. Garoff, but it's more a statement. I would say, like, I really enjoy this presentation and follow his work quite closely, since there are so many extremely useful applications for carbon fiber, and if we could find a way to lower the footprint on those applications, it would be fantastic.
Yes.
So once again, the right material in the right place. There's no one solution. But Niklas and me, we have a long history going back together. So yes, we will continue this discussion.
Indeed. Thank you, Pat.
Thank you, Dr. Mårtensson. Thank you, Dr. Garoff. And Dr. Abushammala, do you have questions for the speakers?
No, thank you very much, and thank you for all the speakers. They're very interesting talks and really well explained. So nothing from my side. Thank you very much.
Thank you, Dr. Abushammala. Since there's no more questions at the audience part, all right, Dr. A. Okay.
Dr. Hatem Abushammala, did you produce CNC or CNF in mass production, and what is the mass production which you produce?
I myself didn't do it on that level. Like, for sure, we did like more or less like lab level or like a bit bigger also. But now there are already companies like mainly in Canada for cellulose nanocrystals and US, and for cellulose nanofibers in Europe. So you can see companies such as Inventia in Europe if you are interested for like CNF. And if you are looking for CNCs, like really big amounts, you can talk to University of May and Silforce. Those guys are like now can really sell them with really decent prices. Like CNF, you can take 1 kilogram for $50, and CNCs 1 kilogram up to $500.
Yeah. Good. Thank you, Doctor. and thank you for all. I invite all of you. We have organized composite conference in Istanbul in April next year, inshallah. We invite all of you and all participants to participate in this conference. I put the link of the conference. It will be worldwide conference in April, inshallah. And welcome.
Thank you very much.
Thank you very much, Doctor. Nice.
Thank you. Thank you. Thank you, Dr. Ayer. Thank you, Dr. Mårtensson. Thank you, Dr. Abushammala. Thank you, Dr. Garoff. So, yeah, thanks for your speech. We truly appreciate that. So,
Thanks a lot for the organization.
Thank you so much. Thank you for joining us. Thank you, everyone. Thanks, all the audience. So, dear all, thanks for participating in the Carbon Tech Global Live webinar. If you have any inquiries, please feel free to contact the DT New Materials. We are always your solution provider. Thank you. Thank you for your watching. Have a lovely day. Looking forward to see you next time. Thank you. Thank you. Thank you, Mr. Dr.